Hi, algebra friends. This is day 2 of our 6.2 notes on exponential functions. So you might remember yesterday we talked all about how to graph an exponential function and looked at some new vocabulary. Today we're going to talk about how to compare exponential functions to linear functions. And we're going to talk about how to recognize an exponential function by looking at the equation in terms of how it looks algebraically. Okay, so let's start by examining some patterns in these two tables. In the first table, we're going to start with the equation y equals 2x plus 3. And we know that this is a linear function because it's written in the form of y equals mx plus b. But let's go ahead and prove that. So when we look at our table, our x values as we move down are increasing by 1. We're going to plug those into our equation and evaluate for y. So 2 times 0 is 0, plus 3 is 3. 2 times 1 is 2, plus 3 is 5. 2 times 2 is 4, plus 3 is 7. 2 times 3 is 6, plus 3 is 9. 2 times 4 is 8, plus 3 is 11. And 2 times 5 is 10, plus 3 is 13. Let's take a look at our second table. Again, our x values are just increasing by 1 as we move down the table. Okay, so same pattern there. We're going to plug these into the function. And remember, we talked about yesterday that you have to start with the exponential part of this function because order of operations says you do exponents before you multiply. So 2 times 0, 2 to the 0 power is 1. 1 times 3 is 3. 2 to the first power is 2 times 3 is 6. 2 squared is 4 times 3 is 12. 2 cubed is 8 times 3 is 24. 2 to the fourth is 16. 16 times 3, 16 times 3 is 48. Yep, and then 2 to the fifth power is 32. 32 times 3 is 96. I don't know why I had to think through that last one so much. Anyway, okay, let's go ahead now that we've completed our tables. Let's look at the questions below. It says, what pattern do you use when you move down your table in each case? So we already determined in both tables the pattern for x is that we're just increasing by 1. Let's look at the change in our y values. So as we move down the table here, we're adding 2 each time, and that pattern continues all the way down the table. Okay, so for the linear, we're adding 2 for the change in y. And remember, we already know that this is a linear function because of its equation. We already also know that linear functions have a constant rate of change. What we want to look at is how do we know if something is an exponential function? So look at our pattern here. This time, instead of adding each time, whoops, and I wrote add, but that's not what we're doing. We're multiplying by 2. Okay, so linear functions have a change of addition each time. Exponential functions you multiply for your change in y. Okay, so that's the difference between linear and exponential. Linear is going to be addition, exponential is going to be multiplication for the change in y. And again, that pattern continues all the way down your table. The next question says, how is this value represented in each function? So if you look, they're asking, how is this value 2 represented in the linear function? And so if you look, it's up here, right in front of the x. If you look at this 2, it's also in front of the x. And remember, the number in front of x is what we call our slope. So in each function, change in y equals the slope. Okay, question 4. Now let's focus on the exponential functions only. Oh, I'm sorry, I didn't finish question 3. How is the starting point represented in each function? Well, the starting point, remember, is the point at which x equals 0. In both of these functions, the starting point is 3. Okay, and so if you notice up here, in our linear function, and you know this from previous work with linear functions, this is our y-intercept, okay? So in both functions, it's going to be represented the same, okay? So that is going to be our y-intercept, and actually that answer goes here. Okay, this is part 1 and this is part 2. Okay. Coming down here, it says, let's focus on exponential functions only. Hopefully you've reached the following conclusion from the table above. So now we're finally seeing the formula that we use to represent a linear function. We read that as y equals a times b to the x. Sometimes you'll actually see that with a multiplication symbol in there just to remind you that you have to evaluate the exponent first before you multiply. So notice again, it's reminding us, this is really important down here, this reminder that A represents the starting point, B represents what you multiply y by, assuming you're increasing x by 1. Okay, so let's go ahead and look at these tables down here. We're going to decide, are they linear or exponential based on what we just learned. So let's look at our first table. Again, you can see that I think in all three of these, the x value is increasing by 1. But over here, this time our y value is decreasing by 2. Remember, decreasing by 2 is the same as adding -2. So therefore, this is a linear function. Remember, in order to write our linear function, we know that this number right here is our slope. Our y-intercept is the point at which x equals 0. So the equation that represents this function would be y equals -2x plus 15. All right, let's look at the second one again. As x is increasing by 1, this time we're multiplying our y values by 2 all the way down the table. So that continues down there. So because we're multiplying our change in y, this is an exponential function. Okay, so we know that this is our, remember that a is our starting point, so that's the point at which x equals 0. The number we're multiplying by is our b. So this function is written as y equals 3 times 2 to the x. Let's look at this last function. This one, as x is increasing by 1, here we're dividing by 2 each time, but remember, we always have to express a linear function in terms of addition and an exponential function in terms of multiplication. So dividing by 2 is the same as multiplying by 1/2. So 1/2 is equal to the value of b, and the starting point of this function is 36, the value at which x is 0. So this is an exponential function. And so when we write this again, our value of a is 36. So it's y equals 36 times 1/2 in parentheses to the x. All right. So I want to backtrack up here. Now that we know the parts of our function, let's go back up here and I want to talk about something really quick. I want to look at our value. Remember, we now know that our formula for an exponential function is y equals a times b to the x. So I want to look at that value of b and how that affects our function, okay? So if you look at our two functions that are growth functions, those two functions on the left-hand side, do you notice that the value of a in this function is 3? Sorry, and I just said a and I meant b, so let's fix that. Sorry, we're looking at our value of b, not our value of a. So this is b equals 3. By the way, in this first function, the value of a is 1 because it's not shown. So it's the same as saying 1 times 3 to the x. In problem number 3, the value of b is 4. So anytime your value of, and again, I almost said a, anytime b is greater than 1, I'm going to clean that up, it's going to be a growth function, Okay, let's look at our value of b in number 2 and number 4. In number 2, the value of b is 1/2. In number 4, the value of b is 1/3. So anytime b is less than 1, it's going to be a decay function, or our graph is going to fall from left to right. Okay, so those are important observations to make, and I think as we move through and get into our next section, we'll be talking about that a little bit more, but I think that's something important that we need to notice. All right, algebra friends, I think you've got everything you need in order to finish up this lesson. So thanks for listening and have